for everyone that's joined in and all your colleagues that may be joining in yet still to come. Thanks for taking the time out of your day. I'm gonna do my best to cover kind of a variety of topics that are kind of NX tips and tricks centric, but kind of focused around the realm of advanced surfacing and some tools that you would use with that and how you would incorporate that into wave workflows and exports. So we'll first talk about some surfacing techniques, then we'll go into kind of fundamental of that. There's a couple of different ways to define splines. We'll talk about then how we analyze our surfaces and what it means to be a Class A surface. And then we'll talk about how we can reuse geometry through various wave workflows upstream and downstream. Talk briefly about kind of a reference model approach that may help streamline your process. We'll talk specifically about a law extension tool and a couple of the Mach 3 tools. And then we'll talk about how to, arrange views for exports of patterns for manufacturing purposes and work instruction purposes. And of course, questions by all means, type them in. We'll try to spend as much time as we can on that to help you out. So the first thing, so surfacing, and so some of this, may be, somewhat rudimentary for you guys, but hopefully we'll get into some broader topics that'll make sense to you. But if you haven't surfaced before, the question is, so how do you define something where nothing is flat, straight, and square, right? So that's kind of the fundamental thing with surfacing. And really, the things, there's different methodologies, but the way I'll focus on today has kind of been my preferred method over the years, designing recreational boats, really complex surfacing. Um, First step is to flatten it. Develop yourself profile and plan curves and then intersect them. And there's kind of a concept here about overbuilding surfaces versus actually building to shared edge curves. And you can kind of see in the back end of the transom of this boat, there's this area where, okay, we've been following a profile and plan intersection curve, but then when we get to the back, we're essentially overbuilding and deviating from that because it's kind of hard to develop exactly that geometry in curves. And then the other kind of fundamental tip is I would say you really need to look at breaking it down. Don't try to do too much at one time. If you've got multiple surfaces, I've color coded these for the multiple surfaces that I constructed in this. Design them in multiple surfaces. Don't try to do, like this rub rail shear line in combination with the whole side, in combination with this spray rail step. You'll have way better luck if you can break it down into your major homogeneous surfaces. And with that, what I thought I would do is show you actually in the NX model of this what that ends up kind of looking like. And one thing here to note, I don't know if you guys know, but in tools, I've got a full assembly here that's all linked. If you select delay model update, delay link update, then you can go to foundational geometry such as the hull molded. We'll open that guy. And now if I make changes here, I'm not going to have to sit and wait on updates of all the rest of the components. But if you're familiar or not here, we're going to show and hide our images. So this would be maybe kind of a typical kind of workflow where an industrial designer may have drawn me a profile and a plan view of his concept for this boat. And so then how am I going to start to construct it? And that's where we're going to look at, okay, I'm going to break this down into 2D. I'm going to create a sketch here for the shear plan. And then I'm going to do a shear profile. And I've actually got this broken up into 2 steps. And this can be really helpful for a number of reasons. But I did this with sharp corners, curves into sharp corners. And then I went and made a shear profile where I added the radiuses. And then I'm going to do a combined projection. And that combined projection is using both the profile and plan, and then putting that out here in a 3D space. And so now I've defined that shear line that is a very complex set of curves in a very simple fashion. And as you can see, it's very true to the artist's intent of what that shear line should look like from a profile and a plan view. And so on to kind of next topic, let's talk about surfacing tools. So NX Design Premium is kind of the new package that's available. It's also still the same, Mach 3 tools, but basically, like my favorite tool here is a Studio Surface. And the reason that it's my kind of favorite tool, I just end up using it a lot. It's more flexible than like a through curve mesh or a sweep, and it does a fantastic job with adjacent surface G1 and G2 tangency. So I'll go into what G1 and G2 are here in a couple of slides, but it gives you a very good Class A interpolation. And just a good example here, if you look at these reflection lines, this is my studio surface interpretation of that whole side, and you can see that those reflections are really clean. This is that same surface with the same control curves, but developed through the use of a sweep tool. You may say, well, why wouldn't I just use a sweep? Why would I use the studio surface? Well, you can see that the sweep is putting a kink here in the center of the surface. And it's just mathematically, I can't dive into all these crazy mathematics that make these things work, but the studio surface does a fantastic job of maintaining a good reflection, good Class A surface. Another one, that we'll touch on, surface flattening. People say, well, why should I buy Mach 3? So yeah, studio surface is a good reason if you're doing surfacing. Also, surface flattening. There's flattening and forming and then reuse of that, which we'll go into later, but those are Mach 3 tools. And then also law extension. And here's an example of where I actually use law extension in the whole form creation. There's different ways to, there's different approaches to everything. This, law extension is an approach for these orange surfaces. Could also be done with sweeps or other approaches, but I'll show you some mold work here later in the presentation that really make law extension a very valuable time saver. Um, So, coming back to spline definition. So when we talk about splines, and I'd like to make this more interactive. I don't know if you all want to drop into the chat if you're familiar with what it means to use a spline by points or spline by poles. Maybe what your preference is in your modeling practices. Do you tend to use one or the other more so than the other one? Um, but talking about what it is here, really, I tend to use spline by points when I'm talking about developing what we would quote, a fair surface. A surface is, not going concave to convex, but really, going very, in one direction without any ripples. And so what that ends up being is that you've got an endpoint and an endpoint. You've got tangency on the endpoint, tangency on the other endpoint. And really what you want to do with this is you want to limit the number of points you have in there, and you want to control the curve parameters by the strength of the tangencies. And then if you did want to say, perhaps like in this case, I'm going from a convex curve in this profile view here to actually a slight concave. So I actually defined a midpoint to that, added a third point to that same spline by points definition. Now, another way to work in terms of like an organic shape, this is what those curves would look like if you did spline by poles. So you've actually got these control points that are out here in space. And you can see here that as I move those control points, I really change the character of that curve. Now, this is maybe less intuitively mathematically defined. What are these points out in space? Well, you drag them. You can go ahead and put some dimensions on them, but you're basically dragging this. This becomes very organic. So if you're wanting to do like a hand grip profile or something that, is a little harder to define, this is definitely one way to approach it. And I'll show you in NX here now what those tools look like. So in the shear plan, so here, so like I say, I like to use the spline by points, and if I double click on the definition of that, you can see that I have a point here in the middle, I have a point on either end, and I've got a G1 tangency on either end. Now, G1 is tangency, G2 is flow. And then the way I control the tangency is I build me some construction curves out here. So I said, okay, I want that to start at about 30 degrees. If I change this now to 20 degrees, you can see that the spline changes. 10 degrees, the spline changes. Um, and now if I were to delete this curve, then the definition loses that tangency, and it has to be it would have to be converted to spline by poles. Um, but then also within that, and then back here, you can see I've got the same thing. I've created a little line here that gets me the angle that I want to start that tangency out. You can also then go in here and it automatically infers a magnitude, but I can specify a magnitude on that first point. Let's say I want to make this thing, 800. There's a very minor tweak here. Let's actually go up to this forward one here. This will probably be more dramatic. Let's make this 200. So you can see that I can tune that curve via these controls. And then if I wanted to also add a G2, which is, the radius, you can see that it's essentially following it's G2 to this line, which is straight. And so now the radius is a bigger radius, starting on that straight. But again, you can fine tune. Um, so then the next thing that we may talk about here is some surface analysis. So like I mentioned, Class A. So feel free to put in the chat. Does anyone know what Class A means? Like I feel like as engineers, unless you really went to like industrial design school or really focused on surfacing, you hear the term Class A. What does that mean? Um, so this ChatGPT did a really nice job for me of, hey, what does Class A surfacing mean? And it gave me some points, and I kind of refined those. But basically, refers to creation of high quality, visually and mathematically smooth surfaces used primarily in automotive, aerospace, and consumer product design, where surfaces must be free from visible imperfections and have perfect continuity. And so that's really kind of the key. And NX has some excellent analysis tools for that. I'm going to actually start on the bottom here. So surface continuity, there's analysis for that. And you can see here in this model, I kind of intentionally left this where I deviate a little bit from a true G1 tangency on one of my developments. Surface boundary, this is really critical. Like, hey, why can't I get this to turn into a solid, right? Well, you actually have to do the surface boundary analysis to see those edges. And then specifically with Class A surfacing, reflection, and this is a big one. So when I turn on the reflection lines, this is really what Class A surfacing means. You can see that all these reflection lines are true and fair. So if I was looking at myself in that mirror, I would be distorted, but I wouldn't be rippled or broken, except for in this area. You can see that these reflection lines start to intersect in a non-continuous manner. And in that model, if we had a little more time, I could show you basically the reason for that is I constructed this main surface, and then I constructed this aft surface as a G1 tangency to the main surface. And even though it's G1 tangent and there is no continuity disruption, it does break the reflection line. When I change that parameter and go to G2, all of a sudden these reflection lines connect in a smooth way. So it's a small detail, but it's important if you're really trying to get that perfect reflection, automotive quality, marine quality. And then the other ones I'll talk about here, tolerance analysis. There's a deviation gauge in NX, and this is an excellent thing. Like I've had a lot of customers talk about, okay, we've got a scanned data that's coming in, as a point cloud and polygon triangles, right? And if you know about that, you really can't, you don't really want to go mill off those polygon models. And so really what you end up doing is modeling clean surfaces using those as reference. And these tolerance analysis deviation gauge are an excellent way. These things operate in real time. So like as I constructed this curve on this particular project, I could change those curve parameters and I could watch the deviation adjust in real time. So I was able to get this dialed in pretty close. And then same thing on a surface. As I rebuild those surfaces and redefine them, I can see where my max deviation is and how it's deviating. So those are very powerful tools for developing either reverse engineered or Class A. I'm going to talk real quick here on wave workflows, and I'm probably going to go ahead and kind of speed up, make sure we keep it within the 30-minute window, and I can always come back and touch on this, but just in case anyone's got to run. But Wave, if you know about Wave, it's incredibly powerful and incredibly robust. And the key thing is you can go up or down the assembly tree to link components from any assembly level. So you don't have to think about, well, it has to be in this assembly. It can be 3 layers deep, up or down, still link. But in the case of a boat, what that might look like, and I could show you in the model, but basically you would have maybe a hull molded, and this would be what I would first model. And then I'd go up the tree into a hull trimmed version, right? And so then I've got a representation of the hull as it comes out of the mold, which all that geometry is just copied over to a new part file. This part file would contain the molded, and then I would start applying my trims. And then I might go from that hull trimmed and go down here into maybe a hull trim pattern, which could live trimmed file. And then I may go the opposite direction here where I may, develop a whole mold, and so I can wave link in that direction. Same thing with the deck. And the only difference here with the deck is going to be foundation is going to be your whole molded, like for the shear line, right, where the rub rail goes. So I'm going to build what they would call an artificial assembly here. I'm going to pull the hole in, and then I'm going to start defining the molded deck, and then again, deck molded and trimmed. And so this is what I would call like a non-physical assembly. The hole molded doesn't actually exist in the deck, but I put it there, and then the step is you wave link as you need, then you exclude it from the model reference set, you change its reference set to empty, and then you can do a parts list ignore in the component attributes, so your parts list is accurate. And then ultimately what that develops is that you've got a trimmed deck inside of a deck assembly and a trimmed hole inside of a hull assembly. And the only thing about this, I'll caution you, avoid circular relationships. So think about if I go take this hole molded and I use it here in the deck molded, I now can't go put deck molded back in hole molded. Okay, and NX will let you do this in the right configuration, but then you would have a circular reference error that you would have to resolve. But what you can do, I've put hole molded inside of deck molded, and then I put deck trimmed, inside of, or deck molded is inside of deck trimmed. I could now actually go and I could put deck trimmed back in here. So part of the reason you do this 2-layer is that essentially gets you kind of the same idea, some of the same modeling benefits as a circular relationship, but it's not actually a circular relationship because you're separated by part generation. And then I've got a quick slide here. You guys can come back to this, and I'm actually, it's a bit of a shameless plug. We're going to do a presentation on this at Realize Live at the 1st of June in Detroit. But just talking about how you can actually be very efficient in your workflow, basically building like multi-body parts that are essentially reference models, quick and easy, and then wave linking those components where they need to go to finalize your design details. Quick slide here again on law extension tools. So again, this is a really big time saver. And so like this is that scenario where I'm making these mold flanges, and I could do this with very few features and very quick. There's a few things about it. Exterior curves, like let me go to the model. Well, I'll go to the model in a second here. When you do exterior curves and everything can sweep in one direction, it works great, like around this bow. When you do interior curves, kind of like what I've got down here, sometimes the law extension tool, you'll have to use patching or other techniques to fill in the corners. So you kind of need to break it up into sections in some applications. But when we look at the NX model here, we'll just get this guy down here to the end again. Um, and what we'll do is go look at the molded, and there is our mold. And so you can see here that I've created this mold, and here's my feature tree. So I've got this linked body. It's giving me an error because I haven't updated it intentionally so. But then this is the extent of my feature tree to get all the way through flanges that are extended, turned out to the side, down and out again, and then a solid body created so you know which direction the orientation is. So it's a pretty short feature tree and a pretty quick process using that tool. And then the kind of the last thing, like I say, I'll touch on here, model views for pattern exports. So this all plays into that whole surfacing realm. So how many of you have a scenario where you're actually needing to create flat patterns either for graphics or for trim operations, maybe by hand, like in the marine industry, we always our workflow would be one where, okay, we've designed all these cutouts that go throughout the boat, and we want them to be in the right place. So we'll put them in CAD, and then we'll create a flat pattern, and we'll export that as a PDF and plot it on a roll format plotter, and we'll go tape it up to the boat, and then we have our hole centers, and we can have accurate drill locations for production on the first article. And then ultimately what we do is we'll use that to create fixtures and jigs kind of by hand, but they're really based out of CAD through a pattern, very accurately placed. And then we have permanent fixturing from there. And I could show you real quick what that ends up looking like when we go to the hull trimmed. And then again in here, using wave linking, I've created a starboard and a port hole trim. And so if we open these things, you can see basically what's happening is that I have a linked body of, oh yeah, I actually linked that from the other side. So we will go here to the porthole trim. And so this is my drawing sheet. And then in the modeling application, we can see that I've linked a face out of that original body. And then I've applied the flattening and forming tool, and then I delete that face. So this is important. You don't go delete the feature. You actually do a menu, insert, trim, delete body. And then you actually delete the body from the tree. And so that way you don't lose the linked face. And then I create a plane. I could talk more here if anyone's interested about how to orient that plane correctly. I create a normal to flattened view that's normal to that plane, and then I orient my drawing to that normal to flattened view, and now I can plot this. And so, kind of a summary of what we talked about. Hopefully, it's been good for you guys. Hopefully, everyone picked up a little something. But the idea when you're surface modeling, start with 2D images, develop 2D sketches, and then develop those into 3D curves, I think is a great approach. There's other ways, but that's what we focused on today. The Mach 3 tools, in particular, Studio Surface, Law Extension, Flattening, Forming, and Reuse. Those are super powerful, really help get this done. Um, the fair curve definition, think about whether you want to use spline by points or spline by poles. And then you can analyze your output with tolerance analysis and surface analysis. And then, make sure to utilize, plan out how you're going to utilize wave workflows so that these complex surfaces, you model them once and then you reuse that geometry. You're not trying to, remodel anything down the chain. And then finally, that view orientation and pattern creation. So that's the presentation for today. I'd open it up for any questions that may have come through.